Hi, my name is Brighten Jiang, and this is my project on improving self-similar solutions for interacting supernovae. You've probably heard the phrase that humans are made from stardust. Well, this stems from the fact that stars have nuclear fusion occurring in their cores, so they nucleosynthesize or form new elements such as iron and nickel. Then, a supernova, or the explosion of massive stars, will shoot the elements that were formed from the star into space. This means that most of the elements on Earth were actually produced by old supernovae. A star is in a constant battle with gravity. The nuclear fusion of new elements pushes outwards while gravity pulls inwards. But near the end of a star's life, nuclear fusion stops providing enough energy because it starts to produce an endothermic reaction. This causes pressure to drop inside the star, and gravity then causes the star to collapse. This is shown in figure 1. You can see the blue arrows of gravity pull inwards, while the red arrows of fusion push outwards. After the star collapses, the star rebounds and ejects the elements it synthesized, which are now called ejecta, and this resulting explosion is called a supernova. Also, before a star dies, they often release mass called circumstellar material, which I'll call CSM from now on. And CSM mainly consists of hydrogen gas, and it sits around the star. So the supernova ejecta will collide with the CSM and produce shockwaves. This is shown in figure 2. The ejecta collides with the CSM, producing shockwaves, and the shockwaves actually give off light. And one way to change the light that is seen from a supernova is to change the density profile of the CSM or the ejecta. And the density profile of an object is how the density changes as you move across something. And again, if you change the density profile of the CSM or the supernova ejecta, it will change how the light is seen from a supernova. The end of nucleosynthesis is unstable, so stars could have some unstable processes that lead to eruptive mass loss for the star. But if the star doesn't go through some unstable processes, more stable mass loss would occur. So the purpose of this project was to explore if stars had more eruptive or more stable mass loss. And to do this, I first needed to make a better model, as current models only input two values for the CSM density profile. I made a new model that can input any value between the two previously used extremes. So as a visual, you can see in figure 3 on the left is a density as a function of radius. So again, that's called the density profile. And this top blue line is one extreme of the CSM, and it's called a shell-like, and it corresponds to more eruptive mass loss. This yellow curve line is the wind-like extreme, and it corresponds to more stable mass loss. So that's what previously models can able to do. And now what I did was to be able to input a much more variety of values between those two extremes. After that, I would take supernova data and use the model to fit a best fit parameters to the data. And using the CSM profile, I could determine what type of mass loss the star had. Making a more robust model, I solved a set of fluid equations that describe the velocity, pressure, and sound speed for a supernova. A similarity transform, which gets rid of units, was applied, and along with Python, which is a coding language, was used to solve the equations. The results were cross-checked with previous authors, and these equations describe how the shockwaves move through space, and they are shown in equation 1 at the top. Next, the luminosity of a supernova is seen because the kinetic energy of the shockwaves are converted to radiation and heating. And this creates another set of equations that describe how the supernova's luminosity changes with time. The luminosity of a supernova is basically its brightness. And the change of luminosity as a function of time is called the supernova's light curve. Now, if you combine these two, you make a model that's more flexible than before, so it's better able to describe different types of supernova. And the model was also checked with current models. Table 1 shows a list of 9 parameters that were added to give more flexibility to the model. And again, the most important parameter was the CSM density profile, which could tell whether the star had a more eruptive or more stable mass loss. Figure 4 shows an example of the improvement that this model made. So on the left, you can see luminosity as a function of time, and this blue curve shows a wind-like extreme for the CSM profile, and the red curve shows a shell-like extreme for the CSM profile. So that's what current models are able to input. And compared to the right, you can see there's a much more variety of shapes if you are able to input values between those two known extremes. So this is useful because developing a better model, it makes the fitting process results in a better fit. So you can see this an example of this in figure 5. The blue dots show recorded light curve data, and it's the same on the left and the right, except on the left with the black fit line, you have a fit that is restricted to one of the extremes for the CSM profile. So that's what current models would fit to. But now on the right, you allow the model to vary between those two extremes, so it results in a much better fit. Now that I know that I have an improved model, I need to obtain the data to fit to. So I used a program to extract the coordinates of 8 documented light curves. These are shown in figure 6. And for each fit, because of the large number of parameters, I started with a hand fit to get a rough estimate of the values of the parameters. Then I used a loop to test through a small range of values for a couple of the parameters, and a Python minimize function that calculated least squares regression. This was used to determine the best fit for each light curve. Figure 7 shows an improvement of the fit from current models. So the dotted black circles show the recorded light curve data. It's the same as the blue dots on the right, and the red and dotted black line in the left show current models trying to fit to the data, compared to the black fit on the right, which shows my model fitting to the data. And then figure 8 showed 2 additional fits. Table 2 shows a list of all the parameter values for each light curve fit. And again, the most important parameter was the CSM density profile, which tells if a star had a more stable or eruptive mass loss at the end of their lives. And table 3 shows a reduced chi-square value, which is basically a judge of how well the fit did to the how well the fit was to the data. And the results are more clearly shown in figure 9, which is a histogram of the CSM values for all the fits. And so you can clearly see that most of the supernova were clustered toward the shell-like extreme. So this suggests that they had some eruptive mass loss near the end of their lives. And so this means that they had some unstable processes during nucleosynthesis before going through a supernova. If given some more time, some improvements would be to add more light curves to test on, because 8 trials is a pretty small sample size, but this is difficult to do because light curve data requires a very long observation time in the telescope. Also, adding more parameters to the model to make it more realistic would be beneficial, but fitting with 9 parameters was already pretty time consuming. And speaking of fitting, automating the whole fitting process could be a possibility because this removes the human input from guessing and checking, and it would definitely take less time. Thank you for listening.